Hello. Welcome to our Thursday class, and this is day three. Yes. Day three, if you're following us in sequence. I am just waiting, I think, for the next 30 seconds or so, and then we can start. Okay, I think we can begin. As I promised the last time, today we're going to be looking at IP addressing. This is a very interesting topic for me, and it is one that I struggled to understand. When I started reading into it, it took me a bit of time to fully grasp the concept of IP addressing, subnet masks, subnetting, classful and classless addresses. And I am going to try and be as slow as possible just to make sure that I cover that topic in detail. And please don't hesitate to ask any questions. I'm going to leave my chat open on the screen so that if you've got any questions, we can be able to address them as we basically go through. Right, so just to kick off, let me see, I think that's this one. Okay, so to kick off our class, these are the topics that we're going to cover today. And by the time we conclude our lesson, we're going to be looking at IPv4 addressing. We're going to be looking at binary, how to convert an IP address from binary to decimal and decimal to binary, and understanding how the numbering system functions. We are also going to be looking at the different classes of IP address. So class A, B, C, D, and E. We're not going to focus much on D and E, but we're just going to glance over it. We're going to look at classful versus classless addressing for us to understand what is the difference and why do we need one over the other. We will probably then look at subnetting. I'm sure many people are looking forward to subnetting because that's one of the most challenging topics that you basically encounter when you're dealing with IP addressing. And then we're going to close off by looking at network address translation. So there's a lot that we're going to cover today. I did not include IPv6. We'll look at IPv6 next week, Tuesday, because I felt that there's a lot of information to cover, and trying to fit in IPv6 when you're still trying to understand IPv4 was probably going to be a bit too complicated. So if you're asking IPv6, that's going to be in the class next week. Right, so without wasting too much time, let us begin. So what is an IP address? In its simplicity, an IP address is basically an address that uniquely identifies a device on a local network. Now, this might not make much sense. So I'm just going to take us back to what we know and what we deal with on a day-to-day basis. I'm sure many of us, if not all of us, have a residential address, where we go to sleep at night. We might not own the house, we might rent the house, but that house, there's a 90% chance that it has an address that it is reachable on. And in my case, this was my old address. So my address was number 18 to 20, Linda Street, Hornsby, and the postcode was 2077, New South Wales. So this address basically identifies a house in a particular neighborhood so that when you want to receive mail from the post, the postman uses that the postman uses that home address to be able to deliver mail. If you were to buy something online, they would use the same address to be able to then deliver your package to your house. And same thing with bills. Now, there's something that is crucial about your home address. Number one, it has to be unique, right? Meaning there mustn't be two houses in the same neighborhood that have the same street name and the house number. Otherwise, it's going to be difficult for you to identify where to send the mail or where to send the packages. So that address has to be unique. So an IP address is basically an address that we use in the networking world to identify devices that are on the network. We spoke about IP addressing, I think, in the first lesson when we spoke about OSI, and we said IP addresses operate at the network layer or layer 3 of the OSI. So when you hear people talking about layer 3, they're basically referring to IP addressing. So we understand we've got a home address. What other address can we, resonate with to be able to understand this concept of IP addressing? So we've got a computer on our network. Our computer has an address of 192.168.0.254. So an IP address takes this format, and that's how it is identified on the network. And this does not only stop at your home computer. Websites, google.com, youtube.com, all these are reachable via IP addresses. And as we're going to go through the class, we're probably going to go through in much greater detail and then be able to look at the structure of an IP address, what is contained, how long is the address, and what is the important information that we need to understand when we're dealing with IP addresses. Right, so we said the first one is, I gave you the example, my home address. The second address that we all use is an email address. And an email address basically helps us receive emails across the world and for people to be able to identify and be able to locate us. And later on, I'm going to break down how the structure of an email address allows for your mail to be routed to the respective email server as compared to other email servers that are sitting on the internet. How does it get routed and how does it get identified, and how important that identification is in the whole process? So the structure of an IP address is, an IP address is 32 bits. Right, so I need to just get my pen out. So 192.168.0.254 is our IP address. An IP address is made out of 32 bits. And what I mean by 32 bits is an IP address has got 32 ones and zeros. And those 32 ones and zeros are broken into something known as octets. And an octet is basically 8 bits. So when we are separating an IP address, we count 1, 2, 3, 4, 5, 6, 7, 8. We put that dot notation. And that's what makes the demarcation factor, the demarcation line on our IP address. And that is continued until we have segmented our IP address into 4 octets. So an octet is 8 bits, and a byte, an octet is 1 byte, a byte is 8 bits. And that is important for us to be able to then understand, because later on, we are then going to convert our IP address into binary and then be able to work out how we can then convert it from hexadecimal to binary to hexadecimal. It's just a second. I'm going to return that. So our IP address is made out of two components. We have what is known as the network portion, and we have what is known as the host portion. So if I were to take back our example of my home address in Sydney that I basically highlighted earlier on, the address was 18 to 20 Linda Street, and that was in a suburb called Hornsby, and the postcode was 2077, and the state was New South Wales, and the country was Australia. And why am I breaking this for you? If I bought something coming from Amazon in the US, how do they locate my home address? The first thing that they're going to look is they're going to look at the country of destination, and the country is going to be Australia. So my package is going to be sent with all the packages that are going to Australia. When the package makes it to Australia, there are different states in Australia, right? So there's New South Wales. This is where Sydney is located. You've got WA, which is Western Australia, where you find Perth. You got Northern Territory. You got Queensland, and you got Victoria. So when my package arrives in Australia, that's step number one. Where it goes from there is dependent on the state. So my package will then be sent with the packets that are going towards New South Wales. And then when it gets to New South Wales, when they want to then distribute it, they look at the postcode, right? This is not the only postcode in New South Wales, there are other postcodes. So there'll be postcodes like 276, 2073, 2088. Out of that, that packet is going to be sent into the postcode for 2077. And then when it gets to the postcode 2077, now it will be at the post office that is in my neighborhood. And from that post office, they would then send it to the respective suburb when they are sending the postman to deliver. And then from the suburb, the postman then finds the street, which leads to the house number, which leads to the unit, which is unit number 18. So an address is critical in the fact that it is used to locate your house in this scenario. That is the same thing with an IP address. An IP address is broken into what is known as a network portion and what is known as the host portion. The network portion basically identifies the network that the IP address or the device belongs to. And the host portion basically identifies the actual host on that particular network. And coming back to our example, number 20 is the host portion of my address. And what do I mean? Number 20 is the house number. Linda is the street. So on Linda Street, there are more than one house. So there are multiple houses. So Linda becomes the network address. So if you are trying to get to my house, you go and look for Linda Street in a neighborhood called Hornsby. And then after you find Linda Street, you find the house number 20, and then you're able to then get to my house. So similarly on the network, when we segment our network into the network portion and the host portion, I'm probably going to erase this so that I can probably then explain this specifically for the IP address. So in our case, let's take the first 3 octets. Remember I said this is an octet, this is an octet, this is an octet, and this is an octet, right? Because I'm going to interchange these terms. So I need you to be very clear as we start. So I said an IP address is made out of 32 bits, and those 32 bits are broken down into octets. And I said each octet is 8 bits. So 8, 8, 8, 8. 8 plus 8 plus 8 plus 8 is equals to 32 bits. All right, so we are clear on that. If you're not clear, please let me know in the comment section and I can be able to repeat, because this is very important for us to understand as we progress on this particular aspect. So our IP address has 4 octets. And if we choose to use the first 3 octets to identify our network address, it means that 1, 2, 3. Okay, I need to raise one more time. So the first 3 octets, or the first 24 bits, are going to identify our network portion. And the last 8 bits are going to identify our host portion. What that basically means is that an IP address of 192.168.0.254 and 192.168.0.25 and 192.168.0.13. All these IP addresses belong to the same network. And why do they belong to the same network? It's because the first 3 octets are identical. So what I've simply done here is house number 20, Linda Street, house number 15, Linda Street, and house number 12, Linda Street are different houses in the same street. It's just that the house numbers are different. However, number 20 Linda Street and number 20 John Street are not houses in the same street because the street names are different. So if we are using the first 3 octets or the first 24 bits to identify the network address, an IP address of 192.168.10.20 is not going to be in the same network as these 3 addresses. Why? Because the first 3 octets or bits are not identical. And that's a very, 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 very important concept for us to grasp before we proceed. And this process that I have defined or described is what we call a subnet mask. All right. I'm going to link around this slide a bit longer because it's very important for us to grasp as we go along. So I'm going to give an example that we all understand. And I don't intend to offend, but if I came to you and I gave you a business card that said John Smith, and I asked you which one is the first name and which one is the last name, it's probably going to be easy. You're going to say John is the first name, Smith is the last name, right? You've probably made that segmentation. Okay, fantastic. If I gave you a business card with this French name, and then I ask you, which one is the first name, which one is the last name? Now, all of a sudden, it's a bit tricky because Yves could be the first name and Saint Laurent could be the last name, or Yves and Saint could be the first name and Laurent would be the last name. So not unless I tell you, right, which of the 3 belong to the first name and which ones belong to the last name, there is no clear defined way of you being able to what? To know. So you need someone to then explain to you what is the first name and what is the last name. And in this example, I would then say to you, the first 9 characters represent the first name, and the last X amount characters represent the last name. So if we count the first 9 characters, we get to this point. So it means Yves sent becomes the first name, and then Laurent becomes the last name. I have to tell you that the first 9 characters define the first name, and the last 9 characters define the last name. Similar with the subnet mask, I have to give you the subnet mask. So in our case earlier when I said, if we're using a /24, right? I know I'm throwing a notation that I've not explained, but just work with me because you might have heard about /24, or you might have heard of something called 255.255.255.0, right? And what do we mean? 255.255.255.0 simply says, wherever you have a 255, I want the number on top to be identical. So whenever you got a 255, the number on the top must match. So if I have 255, 255, 255, what I'm saying is anything that matches on the first 3 values, 192.168.0, is then going to belong to the same network. Whenever you see a 0, I'm simply saying I don't care. That number could be anything from 1 to 254. It does not matter, but the first 3 values must be identical. Now, you're not only going to get /24 IP addresses on the network. So that's why I was saying to you, I don't want you to be fixed so much on trying to guess what the subnet mask is, because that mask has to be given to you. So let's look at a different example. If I change the mask and I make it a /16, I hope you're catching the trend. Remember I said each value is 8 bits, and 8 bits make an octet. So when I say /16, what I'm literally saying is the first 16 bits of the IP address, which is 8 plus 8. So I'm drawing my subnet mask on this particular line. So the first 2 bits are going to be identical for the network, for the devices to belong to the same network. And the last 2 bits can be any number. I really don't care much, but the first 2 are going to be identical. And what is going to be my subnet mask is going to be 255.255.0.0. So wherever we've got 255, it means this has to be identical. And what does that translate to? It means 192.168.10.5 and 192.168.20.5 belong to the same network. Now, I'm sure many of you are wondering, but wait, Tinei, these 2 numbers are not the same. How come they belong to the same network? Remember, our subnet mask has shifted. As long as the first 2 digits match, then they belong to the same network. All right, so I think I've spent much time. We're probably going to cover subnet masks as we go along the way, but I thought I needed to spend a bit of time explaining this part because it's one of the parts that are kind of difficult to kind of get and understand. But anyway, let's progress. I got that. I'm going to return. So let's break down the email address. We all have an email address, And for many of us, our email addresses are either at Gmail, at Yahoo, or at Outlook, which is probably Microsoft. Now, if we break our email address down, our email address is basically split into 3 unique identities. There is the first part, the unique username, meaning Tinei at thenetworkhustle.com, right? That is my email address. So Tinei is the username. And I'm sure when you've created an email address, especially with Gmail, Yahoo, Outlook, if you don't use a unique name, the software will tell you that your name has been what? Has been used by someone else. Why do they do that? Because the user name has to be unique. You can't have 2 email addresses that are identical, because where do you send the email to? So that has to be unique. Similarly, on a network, you can't have 2 IP addresses that are identical on the same network. They have to be unique. So username is unique. The @ sign becomes the separator between what is the username and what is the domain name of the organization. So when you are sending email, you send to the domain of Gmail, and then when the email gets to that domain, it then says, okay, fine, I'm looking for the username code Tinei, and then it will send the email to that particular mailbox, and that's how you receive your emails. I am trying to make sure that we have enough examples that will then help us to then understand when we start getting into the more technical aspects of our IP addressing. So if I gave you an IP address of 192.168.0.254, which part is the network portion? Which part is the host portion? Without giving you a subnet mask, there's no way for you to guess. You can guess to say maybe he wants to make it a /24, which is fine, but there's no guarantee that my subnet mask is a /24. You might guess that my subnet mask is a /8, right? But there's no guarantee that I'm using a /8. I have to tell you what part is going to be the network portion and what part is going to be the host portion. And we do that. Okay, what did I miss? Okay, so we do that by defining what we call a subnet mask. So a subnet mask is what we use to make that demarcation point. And in our case, which I explained earlier on, our subnet mask is 255.255.255.0. The first 3 octets are denoting the network portion, and the last octet is basically representing the host portion. So this is where we draw the line. Anything on the left-hand side, if it is 192.168.0, then it will belong to the same network. But if it's not 192.168.0, then the 2 devices are going to be on 2 different networks. And why is this important? You've heard the concept of a gateway when you are routing traffic on your network. And this gateway, most of the times, is the one that takes us to the internet, right? But we have different, so in your organization, you'll have different departments, right? You got marketing, you got sales, and you got PCs that are sitting here, you got PCs that are sitting here. If I am trying to talk to a computer from 192.168.0.10 going to 192.168.0.255, 0.25, I am going to hit my gateway. Just a second. Okay, I'm going to hit my gateway, and my gateway is going to look at my destination IP address, and it's going to realize that the first 3 octets are identical, and then it says, okay, this needs to go this way. Why? Because you belong to the same network. However, when I'm trying to go to Google or YouTube, the IP address is probably going to be something like 8.8.8.8, which does not match this. So my gateway then realizes, oh, by the way, the IP address is not the same as this. And that means I have to send it to a different path. And then it looks in its routing table to work out if it has a path to that particular destination. And that's what it uses to be able to make that particular decision. So the subnet mask is our identifier to help us make that demarcation point. And as I alluded earlier on, the subnet mask is not always the same all the time. So our subnet mask was 255.255.255 in this example. And I say to you, that's a slash. I say to you, that's a slash 24. And how did we come to that conclusion? 8 plus 8 plus 8 is equals to 24. In our next example, the subnet mask is different. Just a second. Right. In this example, the subnet mask is 255.255.0.0, meaning the first 2 octets, 8 plus 8 equals 16. So that is a slash 16. Keep that value on the top of your mind. We're going to come back to it. Very important, because when you deal with networks on a day-to-day basis, you're going to see slash 24, slash 27, slash 22, slash 16, and you're wondering, what are they talking about? All they're simply saying is the first 16 bits are used to identify the network address, and the last 16 bits are used to identify the host address. Remember, we said our IP address is 32 bits in binary, and it will look something like 1010000.1111000 dot. So when we count those bits, these bits are 16 bits, and thus we call it a slash 16. That's where it's coming from. Very important. So now I want us to do a quick exercise to see if this concept, oh, sorry, I'll probably get to that point. My bad, I jumped the gun. We're going to look at a demo, and I want you to challenge yourself, to attempt to answer the question, to try and see if the concept is coming through. And if you're having challenges, just put a question in the comments and I'll be able to answer it, and I'll be able to then explain. So when we deal with IP addresses, there are 3 types of addresses that we encounter. There is one that is known as a unicast address. A unicast address is basically one-to-one. When one PC is talking to another PC on the network, it's sending packets to that one particular PC, and that is uni, which is single. Multicast is one to many. And a typical example of a multicast address, multicast would be things like Netflix. You got one feed that is coming into the Netflix content servers, but you got multiple houses that are watching the same movie, and that movie is being sent on a one-to-many basis. It's almost, yeah, that's the best way that I can explain your multicast. And then the last one is a broadcast address, which is one to all. So when you broadcast, you are sending to every device on that particular network. Same thing with radio. I mean, you broadcast on the radio. Anyone who's got an aerial is going to receive that broadcast. Whether you wanted it or you didn't want it, you don't have a choice. But with multicast, you have the option of choosing that I want to receive this particular feed, and then you then get the feed if you have made the request to be able to then get it. So now we are going to transition into binary versus decimal. How do we convert from binary to decimal? And I'm just going to start by just walking you through the decimal system, right? The decimal numbering system. I'm sure we covered this at some point when you're in grade 1, between grade 1 and grade 3, right? We learned, no, maybe probably earlier on, maybe in kindergarten, we learned how to count 1, 2, 3, 4, 5, 6, 7, 8, 9. But what we never took time to understand was, how did we get to this decimal system? Dec is 10. And when you're dealing with decimal systems, when you get to 9, right, we get to 10, 10, 11, 12. But from a decimal perspective, you got units that are raised to the power of 0, right? And 10 to the power 0 will be 1. And then you got 10 to the power 1, which is your tens. And then we have 10 to the power 2, which is 10 times 10, which is 100. So your hundreds are 10 to the power 2. And then you have your thousands, which are 10 to the power 3, which is 10 times 10 times 10. So we would read this number as 134. But in actual fact, when you're explaining that number in the real decimal context, it is, I have 100, 3 tens, and 4 units. That's how you get to 134. Because the decimal numbering system follows a particular method, and that method is followed. You get to 10,000, it's the same thing. So let's just work through a few examples just to make sure that that concept is clear. So let us take this number 1025, right? We would read it as 1025. But what are we saying? We are saying we have 1 times 1,000. We have 0 times hundreds. We have 2 times tens. And we got 5 units, or 1 ones times 5. So when we add 1,000 plus 0 plus 20 plus 5, we get 1,025. So to us, naturally by language, we say 1,025. But in the background, that's how you calculate that mathematically in a decimal environment. So why does this matter? It matters because in binary, we are multiplying by 2. Remember, in binary, a bit can only be a 1 or a 0. So our numbers are going to increment in 2s. So 2 to the power 0 is 1. 2 to the power 2 is 2. 2 to the power 3 is 8. 2 to the power 4 is 16. 2 to the power 5 is 32. 2 to the power 6 is 64. And 2 to the power 7 is 128. Our numbers in binary increment in that format. So because our numbers are incrementing in that format, how do we represent? So we have 1, 2, 4, 8, 16, 32, and 64, and then 128. So how do we represent a number in binary? Let's pick the number 10. Right, how do we write number 10 in binary? We ask ourselves, which ones of these numbers do we need in order to get to 10? And let's start from the left, which is 128. Do we need 128 to make 10? No. Why? Because 128 is greater than 10. So we're going to put a 0. Do we need 64 to make 10? No, because 64 is greater than what? Than 10. So we're going to put a 0. We won't need 32. We're not going to need 16, but we're going to need 8. So we're going to put a 1 on 8. 8 plus 4 is 12, greater than 10. So we don't need 4. We're going to put a 0. And then 8 plus 2 is 10. So we need that, and we're going to put a 0. So converting 10 into binary, it's equivalent to 0, 0, 0, 0, 1, 0, 1, 0. This is our conversion of the decimal value 10 into binary. And we use a similar method, if not the same, to then make our conversions when we're dealing with our IP addresses. And we're probably going to look at multiple examples as we go through, because this is a very important concept to be able to then understand, because this is where you're going to learn how to convert from bits to binary and back and forth. So the fundamental thing to know is these two values. We call the exponential value, meaning the increment, right? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. And when you multiply binary values, they tend to double themselves as you increment in the exponential value. What do I mean? 2 to the power 0 is 1, 2 to the power 2 is 2, 2 to the power 3 is, 2 to the power 2 is 4, which is 2 times 2, 2 to the power 3 is 8, which is 2 times 2 times 2. So you go 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 024, 2048, 4096, 8192, 16,000 something. Right. In your mind, that's the first thing you need to be able to do in your mind when you're dealing with binary, right? Just understanding how these values are going to increase, because your number of networks or subnets is going to hinge on your ability to understand that when I'm dealing with the /24, this is what I'm dealing with in terms of the size of the network. When I deal with the /25, is the size of the network increasing or is it decreasing? And we're going to cover that. So you don't have to worry much. We're going to cover that. I just wanted to make us understand. So exponential value on the top, and the numbers are increasing. So in this case, we stopped at 2 to the power 7, but just continue. 2 to the power 8 is 256. 2 to the power 9 is 512. 2 to the power 10 will be 1024. It basically increases as it basically goes through. Let's, right. So let us convert from binary to decimal. And we are going to look at our first example. Yes, we're going to look at our first example. Now I want us to convert this number from binary to decimal. And this is simple mathematics, right? Nothing complicated. Wherever we have a 1, we're going to add. Wherever we don't have a 1, we're not going to add. So in this case, we've got 64 plus 32 plus 8. Right, those are our three values, because these, wherever we have a 1, we're adding. Wherever we've got a 0, we're ignoring. So 64 plus 32 is equals to 96. 96 plus 8 is equals to 104. I hope you got to the same conclusion. So let's try a different number. And I want you to, take a piece of paper, give it a shot, and see if we are on the same page. All right, so I want us to convert this binary value into decimal. 1 0 0 1 0 1 1 0. I'm going to give you 30 seconds to try and convert 100 1011 00 into decimal. And if you are quick with mathematics, feel free to put your answer in the comment section. And let's see if you're going to arrive at the same number. I haven't calculated it. I just wrote that number randomly. But we're going to calculate it together and try and see if we are able to get to the same conclusion. Right, probably going to give another 5 seconds, and then we can then go through. All right. So let's go through. What numbers are we adding? We have a 1 under 128, so it's 128 plus, we've got 1 under 64 plus 64. We've got 1 and sorry, my bad. I don't know, for some reason I was fixated on this one. I'm just going to take a step back and let me just, I need to, okay. So 128, let's just ignore this. 128 plus 16 plus 4 plus 2. What do we get? 128 plus 16, that should give you 6, 4, that's 144. 144 plus 8, 148, 148 plus 2, 150. So 101, 1001, 0110, when you convert it into binary, is 150. Right, if I made a mistake, please just correct me. Okay, I'm just gonna do one more example. I'm probably just gonna clear the screen. One example before we proceed. This time around, I'm not going to write it underneath, so that it's not easy for us, to just look at the screen and be able to convert. So let's convert this number, 1 2 3 4, 1 2 3 4. What is that number in decimal? This time 15 seconds, and then we can probably be able to move on to the next. Okay, so 128, right, first one, 64, 32, and 16. These are the numbers that we're adding. 1, 8, that's 12, 14, 20, so 0, 2, and then this is 8, 11, 12, plus 2, 14, 4, and remainder 1, and then that is 240. So this converts into 240 in decimal. So we've done the conversion from decimal to binary. It's that simple. It might just take a bit of time, but otherwise it should be that straightforward because we are adding. Yeah, I'll probably leave it at that. Let's see. All right, so once again, say decimal value is equal to 64 plus 32 plus 8. And this is how we then make, I'll probably get onto the slide. So we converted just one value earlier on, but we need to then convert our IP address from decimal to binary. And for us to do that, we need to do this 4 times, because remember, this is 1 octet. right? And we said 1 octet is what? 8 bits. And for us to then convert the entire IP address into binary, we have to do that 4 times. So our IP address earlier on was 192.168.10.1. And for us to convert that IP address into binary, we then have to say, okay, what is 192 in binary? And for us to get to 192, we need to ask ourselves, which numbers do we need to get to 192? I have found that in previous classes, the simplest part to make this stick and easy to understand is, imagine you've got 7 coins. This is an $128 coin, $64 coin, $32 coin, $16 coin, $8 coin, $2, $4, $1. And if you're going to buy something worth $192, how many coins do you need to get to 192? Right? So we are going to pick 128 being the highest value. So we're going to need 128. 128 plus 64 gives us 192. So we're going to put the ones under the values that we need. So 1, 1, and then we put zeros all the way. That's how we get 192. All right, so let's convert 168 into binary. Once again, we need 128. 128 plus 64 is 192, which is higher than 168. So we don't need 64, so you're going to put a 0. 128 plus 32 gives us 160, yes. So you're going to need 32. And then we don't need 16 because that number is going to be 176, which is higher than 168. We're going to need an 8, and we don't need 4, 2, and 1. And all those are going to be zeros. And then in the third octet, we're looking for the value 10. And once again, we don't need 128, we don't need 64, we don't need 32, we don't need 16, we don't need 8. Oh, sorry, we need 8. So you're going to put a 1. We don't need 4 because that's going to be 12. We need 2, and we don't need 1. So that's going to be 0, 0, 0, 0, 1, 0, 1, 0. And then the last one, pretty straightforward. We're only looking for the decimal value of 1. So we're not going to need anything else except 1. So it's going to be 0, 0, 0, 0, 0, 1. So when we are done, we will then write our binary values in one line that makes up 32 bits. And this is how our IP address looks like when we convert it into binary. So you should be comfortable enough that if I gave you, or if someone gave you the binary value, you should be able to convert it back into decimal. And whilst it might seem complex, it's straightforward, because all you need to do is you need to split that binary number into 8-bit chunks, and you're going to have 4 8-bit chunks or 4 octets, and then you convert each octet into decimal, and then you get your IP address. Or the reverse is you convert each decimal into binary to get your binary value. And we're going to look at examples that are going to help us reinforce this particular concept. I haven't seen any questions, so I'm assuming everyone else is understanding. If you got any questions, this is the time to ask, especially if you're watching live. Shoot your question, and I'll be able to explain. If I've covered something that you might not fully understand, just raise up your hand, just let me know. I'll come back to it, and we can be able to cover it and make sure that we are on the same page. because later on, I'm going to give you examples. Later on, we're going to do subnetting, and this information is going to be very important for us to understand when we start doing subnetting, because we're going to say /24, /26, /27, and the assumption is you are comfortable enough to be able to then grasp this. I'm not expecting you to master IP addressing and subnetting in one lesson. You can watch the video multiple times, read different sources, so that you can, it might take a bit of time, but the fundamentals are very important. And I'll always reinforce the fundamentals that I feel are crucial for you to understand to make this whole concept of subnetting much more simpler for you to understand. So let us proceed. Let us proceed. Okay, so we have converted. Let us look at let us look at example number 1. We need to convert, and I said earlier on, the first step is rewriting this in our octet format. So we're going to say 1 0 1 0 1 1 0 0. That's the first octet. The second one is 0 0 0 1 0 0 0 0. The third one is 0 1 1 0 0 1 0 0. And the last one is 0 0 0 0 0 0 1 0. So that's the first step, just writing down. The next step is in the mathematics part, addition. 128 plus 32 is 160. 160 plus 8, 168 plus 4, 172. So the first octet is 172. The second octet is 16. We only have one, so it's only 16. 32 is equals to 96. 90, then this one is equals to 2. So what is our IP address? This is equivalent or equals to 172.16.100.2. Is that simple, right? That's how you convert 172.16.100.2 into from binary into the IP address and doing the reverse. As long as you understand this table, that is your pivotal table when you're doing binary conversions. Because in your mind, you should tell yourself 1, 2, 4, 8, 16, 32, 64, 128. So if I have a value in my mind, I can then say, okay, fine, do I need 128? If I need 128, I'm putting a value under 128. So master this increment in value, because that is going to be very important. So let us confirm to see if our answer was correct. And our example is 172.1600.2. So that is the IP address. Let us do another example. Now, I'm probably going to give maybe 45 seconds. The key, guys, is practice. It's challenging yourself to try and get a piece of paper and, try it, so that when we get to the answer and your answer and our answer is correct, then fantastic. We know that we're on the same page. If your answer and the answer that I come up with are not matching, that is the learning process. Sometimes we get things wrong, or maybe I might get things wrong on my end and you will be able to correct me. So 45 seconds, let's give this one a try and let us see if we can get this one right. I didn't put a timer, but yeah, probably 10 more seconds to go. All right. Oh, sorry, that was me. I was just sending a message on the Facebook group. Yeah, I'll probably take this time to not necessarily advertise the Facebook group, but we do have a Facebook group, and it is The Network Hustle. The Network Hustle? Yes. At The Network Hustle. I think so. Yes. If you want to get real-time updates, feel free to join the group, and we can then be able to discuss, beyond this boot camp. If you've got any questions, I will probably be appearing more on the group and, doing weekly sessions for just generic questions that are related to networking, whether it is certification, what the future looks like, challenges that you're encountering at work that you might need assistance on. We all need some help at some point. So the group, feel free. You're not being forced to join, but yes, I'll probably be present on that. But anyway, back to our topic. All right, so let's convert one. So you start by writing, right? The first part, just write 1 0 0 0 0 0 0 0. And this is four zeros, 1 2 3 4 1 0 1 1. And then this one is 6 zeros and a 1 1 1 2 3 4 5 6 1 1. And then the last 5. So it's 1 2 3 1 1 1 1 1. Okay. So we've written the first one. By virtue of this is 128. So that's going to be 128. That's simple and straightforward. 8 plus 2 plus 1, that's going to be 11. 2 plus 1, that's going to be 3. And then 16 plus 8, which is 24. 24 plus 8, 28 plus 2, 30 plus 1, 31. Right. So our IP address is 128.11.3.31. That is the IP address that is represented by that particular binary value. Let us check to confirm that that is correct. Just gonna go to the next slide, and there we go. 128.11.3.1. So if you came to this particular conclusion, fantastic. Converting from binary to decimal or binary to IP address means you get it. It does not get any worse than this. This is all it takes, converting from binary to decimal. So now let's do the reverse, converting from decimal back to binary. We've probably covered that at some point, but we're gonna go through once again. The process is the same, we're just doing it in reverse. So for us to convert 192 into decimal to binary, we need to ask ourselves, which values do we need? And this is where the concept of the money starts making sense. If this was a $128 note, a $64 note, a $32 note, ask yourself, if you're going to go to the shop and buy something worth $192, which of these denominations do you need to get to 192? And in our case, we need 128 plus 64. And we said earlier on, you put ones under the values that you need and zeros on the rest. And that's how you convert from decimal to binary. So this is our conversion from the decimal to binary. For 172, similar process. We need 128, we need 32, we need 8 and 4. and we get 172. For 16, we only need 16 as the only value. For 10, we need 8 and 2. And for 1, we only need the value of 1. And that is how we convert our IP address into binary. In this case, there are no dots. Why? Because when it becomes ones and zeros flowing through the network, there are no dots. The dots are for us when we are representing and reading it in a notation that makes much sense. But for computers, it's going to flow as just one string of ones and zeros, and it just knows how to then make the demarcation point. So I don't know if there's any questions, because that is the end of decimal and binary. As we go later on, we're going to be looking at other aspects, but in as much as decimal and binary is concerned, that basically is the end. So I hope you're comfortable. If you're not comfortable, please don't hesitate to ask questions, and I'll be able to answer if there's anything that I might have missed or that you might want to understand. And I will, maybe in the next coming few weeks, I'll probably do some quizzes that I'll come online, and we'll just do binary and IP addressing only, and we just do questions on binary and IP addressing, just to make sure that we sharpen, our mind. They say repetition deepens impression, right? The best way to learn is to repeat something multiple times until you get to a point where you understand it. Okay, so let us proceed into public versus private addresses. We have IP addresses on the network, but you've got different types of addresses. What are the different types and why do we need them? A couple of years back, when you wanted to go on the internet or go on the network, you had to write a letter to an organization that was known as the Internet Addressing Something Authority to ask them for IP addresses to use on your network. And because there wasn't many devices on the internet, you were given a public block of IP addressing. So they would give you a chunk of maybe 1,000 public IP addresses that you could then take home and configure on your devices. And your devices would then become online. The challenge, though, was that the internet grew faster than what they were expecting. And they realized that they were going to run out of IP addresses, because for you to talk on the internet publicly, you need a public IP address. And if every device on the internet was to have its own IP address, then we would not have enough IP addresses to cater for everyone. The IPv4 IP address scheme or range only has 4 billion IP addresses available. And the world population at the moment is more than 6 billion. I think the last time I checked, I think it was 6 or 7 billion. And not only do we all have one of these devices, but we have a smartphone, we have laptops, we've got computers. So an average person has plus or minus 3 devices. And if we were to take 1 billion or 2 billion people being predominantly participating on the internet and each having 3 devices, it means that we would need 6 billion IP addresses to be able to cater for that. And that was not going to happen. So what the Internet Addressing Authority then did is they came up with what they called private addresses. And these are addresses that are not routable on the internet, Right, so public IP addresses are addresses that you can route on the internet, and private IP addresses cannot be routed on, on the internet. So this is what they said. If you're going to have a computer on the network and that computer does not need to be on the public internet, we are going to come up with 3 subnets that are dedicated to just private addresses. And these subnets are the ones on the right-hand side, the 10.0.0.0, 172.16.0.0/16. Remember earlier on I said the slash notation. So when I say /8, I'm assuming you understand that we are talking about the first 8 bits. So the first 8 bits must be identical. The last 24 bits can be different, but because they share the first 8 bits, which is a 10, they are going to be on the same network. 122.16, 192.168.0.0. And these IP addresses are very common because many of us on our home networks, you have one of these 3. So when you get a modem from an internet service provider that gets you to connect onto the internet, you're going to be using one of these 3 IP addresses. These IP addresses can then be identical on different networks. Why? Because they are private to a particular network. And coming back to my example, the house number 20, right, can be used by every street in the world. And what do I mean? You can have number 20 John Street. You can have number 20 Peter Street, or you can have number 20 Gushungo Street. Right, Gushungo is that's my totem, so just excited about it. Anyway, so the number 20 can be shared, but it is the street name that decides where the number 20 belongs to in each neighborhood. The same is in your organization. Company A can have a network of 10.0.0.0/8. Company B can also have a 10.0.0/8. And there's no conflict. Why? Because these IP addresses are not routable on the internet, which means that internet routers, when they see a subnet of 10.0.0.0/8, they drop that traffic. They don't bother routing it because they are private IP addresses. So all of us can have this small portion of IP addresses that we can use for our internal networks. I am going to just double check my phone. If you've got an iPhone or Samsung, just go to your mobile settings and try and see what IP address you have. I don't even think I can probably find mine, but anyway, what I know is on my wireless network, and I'm probably going to show you on the screen just now, I am getting, let's try and see if you can see that. Right, you can see that my IP address is 192.168.0.8. Right, and that is similar to 192.168.0.8. Sorry, it's supposed to be /24. So those are the 3 classes of addresses, which later on we're going to talk about class A, class B, class C. We are basically referencing to those. So they came up with the private addresses, and then they came up with the public addresses. The public addresses are these addresses that can be routed on the internet. And a typical example of a public address is the famous Google DNS 4.2.2.2. That is a public IP address. Let me just pull my command line onto, right, let's do this practically. So cmd, I'm going to press enter, and I'm going to put that on this screen so that we can be able to see. Just try and zoom this. Let's edit that, properties. All right, let's increase the font to 24, make it a bit bigger. All right. So let's look for Microsoft. Right, so let's ping Microsoft.com and press enter. And the IP address for Microsoft that is showing up on my PC is 20.112.52.29. And that is a public IP address. So that's the public IP address for Microsoft. Let's look for another one. So you can either do ping or you can do something known as an Nslookup if you're using a Windows machine. So Nslookup, and let us look up google.com. Let's find out, if I'm sitting in Australia, what is the IP address for google.com? And the IP address is 172.217.167.110. And that does not match our private IP addresses. So that's a public IP address. So we've got public IP addresses, we've got private IP addresses. When I did an Nslookup, you notice that there was this value that came up, this 192.168.0.1. That is the gateway from my home internet. So from my PC, I have an IP address. I'll probably just double check. My gateway has an IP address of 192.168.0.1. And then my gateway then goes to my internet service provider, which then takes me to the internet. So I can then do what is known as a trace. In Windows, we call it trace set. And I want to trace google.com. And I want to say, what path do I take to get to the Google servers? And you will notice that I hit my gateway first, which is 192.168.0.1, which is a private IP address. But my next hop goes to my internet service provider. In my case, it is Optus, and that has an IP address of 49.192.48.1. And I'm probably going to stop my trace at this particular moment. If I want to check the IP address of my PC, I type the command ipconfig. Right. So if you're, just in case you're wondering, what it is that I'm typing and, how do you get to the point of knowing this? We are going to cover this in the course. I'm just doing this a bit early just to try and illustrate a particular point. Now, I have a number of virtual machines on my computer, and those virtual machines have got virtual network cards. And we covered that in the previous lesson, right? We said virtual machines will have its own virtual NIC, and the virtual NIC will have its own IP address. And this is a typical case in point. I have multiple virtual adapters. So I've got this VMnet 1, virtual machine network number 1. I've got this VMnet 14. I've got this, and then I've got, this is my Wi-Fi, my LAN Wi-Fi, or my wireless Wi-Fi at home. My virtual NICs, the IP address is 192.168.165.1. Remember, we spoke about the subnet mask. This is the subnet mask. So that subnet mask then identifies, it's a 255.255.255.0. What does it mean? The first 24 bits are denoting the network ID, and the last 8 bits are denoting the host ID. So what it means is this network, 192.168.165 192.168.0.x and my home network 192.168.0.x are not in the same subnet. Why? Because the first three octets are not identical. My home network is 192.168.0, but my virtual network environment is 192.168.165. And this, what I've just demonstrated now, is real life. This is what you encounter when you deal with networks on a day-to-day basis, because you need to then translate when you see an IP config output and you see an IP address given there and you look at the subnet mask, you need to then be able to denote, are they belonging to the same network or not? And in relation to what I'm trying to troubleshoot, where do I start? Because that's the most important part. We learn all these things so that when we are troubleshooting issues, I can be able to figure out that, oh, by the way, these are not in the same network. And because they're not in the same network, I'm going to need a router or a layer 3 device that takes me from one network to another, because you need something that routes between two networks. If two networks are sitting, they can't belong to the same subnet. You need to go to your gateway. What example can I give that can probably make this much clearer and make much better sense? I can't find an example immediately, but I'll get to one. But anyway, I just digressed a little bit just to give you real life perspective of, and this you can do on your computer. You don't need to wait for anyone's PC. You can do this on your computer. Look at your own IP address, look at your subnet mask, and ping your gateway, ping your ISP, do a trace route, and you can see the hops as they go along the lines. But all I wanted to demonstrate was the fact that when you, let me just close this. We have two sets of addresses, private and public. Private, anything that starts with the 10.0, 10, anything that starts with the 10 is a private address, because remember the first 8 bits. So anything that's starting with the 10, private address. Anything that starts with 172.16/16, and we're going to talk about that later on. So anything from 172.16.0.0 to 172.16.255.255, any value in between is considered a private address. I am going to just give you one more hint before we progress. For some, you might know about it. For some, you might not know about it. But they are online. They are online subnet calculators. Right. So you can go online and look for an IP subnet calculator, and you can find these online. I'll probably just try and zoom this to make it a bit bigger. That's probably too big. Okay, so if you're in doubt and you're not so sure, you can come into one of these ones and say, okay, fine, I've got an IP address of, let's say, 172.16.23.25, and it is a /23. Or let's make it /24. Let's make it easier. /24, and then I'll calculate. And what it will do is it will tell me what is the network address, what's the range of usable IP addresses, what's the broadcast address, and what is the subnet mask. We're going to cover this, but I just wanted just to show you that you can find these things online and you can be able to use them for practice. All right, so back to our slides. So anything that's not a 172.16, 192.168, or 10 then becomes our public IP addresses. And these are the ones that can be routable on the internet. So when your internet routers, when they see an IP address with a destination that is not any of these three, then they can then route those packets going to a particular direction. We have covered a lot. Blessing, thank you very much for the compliment. Yes, Gushungo is here. I'm sure many of you might not, fully understand, but speak to anyone from Zimbabwe, they'll tell you that our totems mean everything to us. They are our identifying factor. We bask in the glory of our totems. But let me not digress. Just have a 10-second questions. I don't know whether that we are understanding, everything else is good, or you're like, man, I don't know. Anyway, maybe questions will come later on. But we'll then, the structure of an IP address, we have covered binary to decimal. We looked at private versus public IP addressing. And now we're going to look at the different classes of IP addresses that we basically find. And this example to me was the one that is more befitting, because if you have flown before, many of us in this class or watching this video, I'm sure we fly economy class. And an economy class, you find the most number of seats in aeroplane, and the seats in economy are close to each other. It's economy. We can't afford to buy the expensive tickets, so we all sit in economy. However, if you have a little bit of money in your pocket, you upgrade and go into business class. In business class, these are the guys who look down on us in economy, and in business class, the seats are more spacious and there are less seats in business class because they want to give you enough room. And then there's the one class that I've never flown in first class. I hope at some point someone will be willing to donate that I can fly in first class, but this is the class that we all wish we could fly, right? So maybe in a plane, the first class might have about 8 seats, and these are the seats that can recline and turn into a bed. You've got the bar in the aeroplane where you can then go and drink and everything, all the nice things on a flight. You'll probably find them in first class. So what does that have to do with IP address classes? We have 3 classes of IP addresses. We have a class A, class B, and a class C. And depending on which class it is, that determines the number of IP addresses that you can be able to use. So a class A IP address has fewer networks, but has more hosts per network. Now, if ever you needed a time to concentrate, this is the time, because I'm going to say things that might take a bit of repeating for you to then understand. A class A address uses the first 8 octets. Uses the first 8 bits. It uses the first octet to define the network address. And mathematically, we take that 8 bits, we multiply it, and that gives us the number of networks that we can have on our network. And then we take the last 24 bits and we multiply them, and that will give us the number of hosts per network. I'm going to give you the formula, or I'm probably just going to put the formula here, but we're going to cover it later on in more detail. The formula is 2 to the power x is equals to the number of networks, right? Where x is equals to the network ID, right? So what am I saying, or what have I said? We take the number of the network ID that's identifying the class in question, and we raise that to the power 8. So 2 to the power 8 is equals to 128. So we can have 128 networks. But each network has the formula for the host on that network is 2 to the power y minus 2 is equals to the number of hosts on the network. And how do we find y? Y is equals to the host ID of that particular subnet. So we use the first 8 bits as the network ID, and we're using the last 24 bits as the host ID. So then y is equals to 24, because remember, x plus y should give us 32. So if we have used 8 for the network, it means we have 24 remaining, and 2 to the power 24 minus 2 then gives us 16 million hosts per network. So when you are using a /8 IP address, it means that we can have up to 128 networks, and each network will have up to 16 million hosts. And what does that mean? What that basically means is there are few organizations in the world that have /8 IP addresses. And these IP addresses were allocated to internet service providers, right? So they get one block, and then they then carve out smaller subnets and then give those subnets to you and I as we pay for internet and use their network. Because for you and I to go onto the internet, we need an internet routable IP address. So the ISP would get the bigger block, and then they would then subnet into smaller blocks, and then they sell those to individuals. Right. We are going to then do this formula part later on as its own topic, but I just thought I'll introduce that and be able to then cover. So a class A address, right? What we need to know when we say class A, the subnet mask is 255.0.0.0, or in notation format, it's a /8, meaning the first 8 bits or the first byte or the first octet is basically representing the network ID, and the last 24 bits are representing the host ID. A class B address is one where the first 16 bits represent the network and the last 16 bits represent the host. So how many networks can we have? 2 to the power 16. And 2 to the power 16 is equals to 16,000 networks. Now remember earlier on I said to you, learn to count in twos. So let's go and see if that makes sense. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 40968192, and that probably takes us to 16,000 plus. If we count from here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 plus the 0. That takes us to 16. So a slash 16 then gives us 16,000 networks. And in that network, we can have up to 65,000 hosts per network. These are very big subnets reserved for bigger organizations. So I said to you before, you'd write a letter, go to the Internet Addressing Authority and ask them for a subnet block. And they would then give you a block of IP addresses based on what you require. So organizations like Facebook would probably then would be allocated some of these addresses. What I did not mention earlier on is, because on a class A, you are getting 126 networks. It means every IP address that starts with 1 or any value between 1 and 126 is then classified as a class A address. Any IP address that starts with 129 up to 191 is classified as a class B IP address. And then any address that starts from 192 up to 223 is classified as a class C address. So by merely looking at an IP address, you should be able to then identify whether it's a class A, class B, or it is a class C type of IP address. So we have class A, class B, and then the third one is a class C IP address. And the class C IP address uses the first 24 bits to denote the network ID, and the last, and if we put that in our formula, 2 to the power 24, we come up with 2 million plus networks. So you've got more class C networks, but each class C network has got up to 254 hosts. So the networks are much more smaller, which is why most of the home networks that you're going to find are going to be sitting on 192.168.0, 192.168.1, or anything along that assortment, because that is the smaller carved subnet that we can then utilize for smaller organizations. It's still not perfect, but that is how as close to being perfect as we had with the default standard of subnetting. And we're going to look at classless versus classful to then understand what was the problem with classful IP addressing. And what I've just explained to you right now is what we call classful IP addressing. And classful IP addressing is when you subnet based on the original IP address value, right? So a class A IP address is a /8. A class B is a /16. A class C is a /24. When you subnet on those boundaries, you are subnetting at the classful boundary. And the challenge with that is sometimes you don't want, so let's take my home network, right? I have, how many devices do I have in this home network? Not more than 10, right? That's including my TV and other devices that go on the network. So I have a class C address that I'm using. I showed you earlier on my IP address is 192.168.0.0/24, and I'm using 10 addresses. Now, how many IP addresses are in a /24? We said the formula was 2 to the power X is the number of networks and then 2 to the power y minus 2 is the number of hosts on each network. On a /24, we are using the first 24 bits for the host ID. So that gives us 2 million networks, but each network has got 254 hosts. So which means that my network has got the capacity to support 254 hosts, but I'm only using 10. So in literal sense, I'm wasting 240 IP addresses. Now, it won't matter in my home network, right? Because I really don't need the other 240, and it's a private IP address, so it affects no one. But in a corporate environment where you got multiple subnets that you are using for different devices, for different VLANs, for different server infrastructure, this leads you to a point where you can easily run out of subnets that you can allocate because you're not being conservative. The smallest subnet that you can get is a /24 with 254 hosts, but maybe you're just putting people in sales, and that department has its own VLAN, and that department has got probably 10 people. So now sales consumes a /24, marketing consumes a /24, you're trying to put a printer subnet, another /24, and it becomes a bit messy because you'll have too many subnets, which then in turn affects your routing, because then you'll have too many routes in the routing table. Yes, you can summarize, but I'm just trying to illustrate a point that this was a problem in itself, and we're going to find out how that problem was then fixed. And the last two is a class D and a class E address. A class D is a multicast address, and this is used for multicast traffic. Some of the routing protocols use multicast. Routing protocols such as EIGRP, they use multicast, so they operate in that space. And then class E was basically reserved, not to be used. I have not encountered a class C. Sorry, class E IP address. So what I want you to take from this slide is this part. I don't know why I get caught up in this. Okay, this part is the most important part. Just be able to know that a class A, first 8 bits network ID, class B, first 8 bits network ID, class C, first 24 bits network ID, and the last. So /8, /16, /24. I'm sure at some point you've encountered these notations as you have interacted with networks, and you've wondered how to look at an IP address and try and work out what's happening. Anything that starts with the 10, by the nature of classful addressing, is a class A address. Anything that starts with 172.16 is a class B, and anything that starts with 192 up to 223, it is a class C. So by just merely looking at an IP address, if you're using classful boundaries, you can identify. However, if you're using something known as classless, then it is not as obvious as you might want it to be. Thank you, Meta. This video is helping me out so much. I'm very happy that it is helping someone out there. Yeah, it took me getting up to the 1 hour, 45-minute mark for someone to say, yeah, it's helping. So that's good. I'm excited. I can go to sleep peacefully tonight knowing that this video is helping someone. So yes, this is important. Not to keep it on a piece of paper, but keep it in your mind. Just be able to know class A, class B, class C. So if I ask you, what's a class A IP address? Anything that starts with 10. What's a class B? 172.16. What's a class C? 192. to 223, any of those addresses would then be a class C. I'm going to come up with a quiz. It's going to be a bit difficult, but yeah, if you're able to pass it, then you should be able to go and pass anything relating to IP addressing as you go write the exam. And I'm spending much time on this topic because I've been burnt a couple of times, in a work environment because of subnetting. Sometimes you don't get the subnetting correct. You then don't identify particular traffic. Your firewall rules are not identifying the traffic. So you're denying what you're supposed to be permitting, or you're permitting what you're supposed to be denying, and that causes chaos on the network. So very important to learn and be able to understand. Okay. So that part is clear. Okay, so there we go. Class A, 128 networks, 60 million hosts, reserved for large ISPs. Class B, 16,000 networks, 65,000 plus or minus hosts, reserved for big corporates. And then Class C, this is where most of us probably then fit in. So now this conversation of classful versus classless. And the classful boundary was a problem, right? A company goes and makes an application to the Internet Authority for some IP addresses. And this is why private addresses were then introduced, because the dilemma was you go and make your application, they could only give you one of three categories, a class A, class B, or a class C. Right? If I give you a class A, there are only 128 networks that are class A addresses. So if you take that 127 left, how many hosts do you have? 16 million. Do you have 60 million devices on your network? Maybe not. Right. So you have organizations that were involved at the beginning of the internet that took some of these large subnets as a sectors that they're not using, and there isn't enough, right? So this was the dilemma. If they gave you a /16, which is a class B, still 65,000 hosts, how many businesses have got 65,000 devices that need to talk to the internet? Maybe not many, right? So they had to find a way of making this equation more equitable so that they could preserve. Remember, they're trying to think about the future, right? So they need to preserve IP addresses. So they came up with something known as, I'm still going through the classful. So this is my example. Imagine you walk into a shop, and in that shop, there are only three sizes for jeans, right? Either extra large, large, or small. There's nothing in between. So if you're like me, you're not too big, you're not too small. If small is not good enough, then you have to buy a large, but then the large is too big. So now you have to go and find a tailor to then alter those jeans. Clearly, that was not going to work. So what did they do? You've got shops that have every size. You got small, you got medium, you got large, extra large, extra, extra, extra large, 31, 32, 33, 34. There is a size for everyone. Why? Because in real life, that's what we need. We need a shop that caters for our need. So they needed a way of being able to come up with a way of allocating IP addresses that made sense, where we could give you the number of IP addresses that you needed without wasting too many IP addresses. And ladies and gentlemen, that takes us to what is known as classless interdomain routing, or CIDR. So what is classless, and what problem was it coming to solve? It replaced the old system of class A, class B, and class C. And how did it do that? They used something known as variable length subnet mask, VLSM, right? That's a mouthful all by itself. Variable length subnet masks. So what is variable length subnet mask? Variable length subnet mask, in simplicity, or in simple terms, I give you what you're looking for. So what do you mean I give you what you're looking for? Let's go to our whiteboard. So I say to you, my home network is 192.168. 20.0.0/24. I have 254 addresses that I can use. I'm only using 10. Right, so I'm wasting 240. So imagine if this block was a public IP address block. It means that when I purchase that block, I have wasted 240 addresses that other people need. So what does classless interdomain routing do? It says, okay, how many addresses do you need? I say, I think I'm going to have 10 devices on my network. Okay, you have 10 devices. We are going to give you 10 IP addresses. And we're not going to give you the whole /24 subnet. So, okay, you're going to give me 10. Okay, so how are you going to calculate it? And remember the decimal to binary conversion and binary to decimal conversion. They then say to themselves, okay, 128, 64, 32, 16, 8, 4, 2, and 1. So what numbers do we need to get to 10? We're going to need an 8 and a 2. And the rest are going to be zeros. I want you to work with me. Work with me on this one. Okay, cool. So then they give me this. And then we convert this into the decimal value. And what that, I'll hold on to that one. I'll get to that part and I'll probably explain it in much greater detail. So in this case, if I went to the internet company, they would then give me a /28. So they'll give me 192.168.0.0/28. So they'll give me a /28 address. And that would give me only 16 IP addresses. There are 16 IP addresses, but 14 that are usable. So instead of me wasting 240, I'm only wasting 4 because I've been given the chunk size that I basically need. All right, so let us look at CIDR and the slash notation and what that basically means. In our instance, we've got an IP address 10.180.96.11, and that's a /22, which is, we're no longer dealing with /8, /16, /24. We're now using a variable length subnet mask, meaning that our length of our subnet can now float to any number other than the 3 classful boundaries. Because remember, classful boundaries were 8, 16, and 24. But classless, which is variable length subnet masking, you can choose any number to be your variable length subnet mask. So what does that mean? It basically means that the first 22 bits in our IP address is going to denote the host ID. I'm going to say this slowly and I'm going to say it again. When we say /22, what we are saying is in our 32-bit address, which is, we spoke about earlier on, let me just get my pen, 1 2 3 4 1 1 1 1 0 0 0 0 0 1 1 1 0 0 0 0 1 1 1 1 1 2 3 4 5 6 7 8. This is our 32-bit address. You're with me? When we say /22, we are going to count 8 plus 8 plus 6, and we are going to draw a line. I think my line is drawn. Let me just look for a different color. Just bear with me. I need to be able to explain this part much clearly. Okay, I've got a different color. So the first, I need to come back to my pen. Okay, the first 8, the second 8, and the third 6. So I draw a line here. Anything on this side becomes the network ID, and whatever is the remainder becomes the host ID. But the total number is always going to be 32, or the maximum number is always going to be 32. So, very important concept. So this network can be a /22. The next one can be a /27. And when it's a /27, what are we saying? We are saying the first 27 bits become the network ID, and the last 5 bits become the host portion of that particular IP address. We are now able to slide and fluctuate based on what it is that we are trying to achieve and how many addresses we basically need. Now there's a table that I have, and I'm going to encourage anyone who's serious about understanding VLSM to master this table in their mind and be able to, at bare minimum, identify the range of the subnet that we are dealing with when we say /27, when you say /25, when you say /24. In your mind, you should know how many hosts we are looking at in that particular subnet. And remember earlier on I said to you, just learn to count in twos. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. Because if you look at our table, you'll notice that we have the subnet mask, right? Which is 255.0.0. I'm starting from the top. So if you're wondering where I am here. Okay, let me just make sure that I come back to my original color. Right, and then I'll come back here. All right, so we're starting from the top, right, going down. 255.0.0.0. The CIDR value is a /8. And we said the number of networks, 16 million, sorry, the number of hosts per network, 16 million. The number of networks, about 126. And then when you go to the next network, it becomes 255.128.0.0, and that becomes a /9. So what has happened? What has basically happened is, remember, we said a /8 address uses the first 8 bits to denote the network ID. So the first 8 bits, which is 1, 2, 3, 4, 5, 6, 7, 8, dot, were used to denote the network ID. And then we moved into a /9. And that /9 means that we're using the first 9 bits to denote the network ID. However, when we wrote our table earlier on, we said 128, 64, 32, 16, 8, 4, 2, 1, and then we put a dot, because now we're making the differentiation between the first octet and the second octet. And we called it a /8. Now, when we call it a /9, what's the next value that we're going to encounter? That value is 128. So when we put a 1 here, we are saying we are going to be using that 128. That's why you find that the next value here is 255.128.0.0. And that becomes a /9. Look at what's happening to the number of hosts per network. It's reducing by half. So from 16 million, now it goes to 8 million. How many bits remain for the network ID? Sorry, for the host ID, we've got 23. And how do we get to 23? It's 32 minus the CIDR value. It gives you that. So 32 minus 9 will give you 23. And then when you go to the next one, it's 192, meaning we're now using 64 and 128. And we said mathematically, when we add 128 plus 64, we get 192. So now our subnet mask is sliding based on the needs that we have. I started with the class A, might be difficult to understand. So let us look at a class C, which is at this point, and that is much more easier for us to then grasp because it's a /24. However, if we needed to carve it into something much more smaller, we then borrow bits. Hold on to that term, I will explain it, but we borrow bits. And in the borrowing of bits, what are we doing? We are decreasing the size of the network, but we are increasing the number of smaller networks that we're then able to create. And in the process, we are then doing what we then deem subnetting, which you're probably going to cover in the last segment of this class. So this table, I would encourage you to at least master up to this point. Anything going down, just in your head, you should be able to say 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, and 16384. It's very important because the more you keep it in your mind, the easier it's going to be when you then break down and cover this content. I think, let me just double check. I might have some questions on the Facebook side. So I'm just checking if there's anyone who is raised. I see some notifications. Okay. All right, no, nothing important. That's all good. We can continue. Just making sure, just in case someone might have. Where's my cursor? I just lost my cursor. There we go. Cool. All right, so I'm going to erase that. And let's go to an example. So in this example, we have gone to our ISP and they've carved for us a block of IP addresses. Yes. Okay. So let's break down this example. So we've gone to our ISP and we said to our ISP, we want some internet addresses because we want to go online, and then they give us a 192.168.100.0/28 address. What does that mean? It basically means that the first 28 bits are going to be used to denote the network ID, and the last 4 bits are going to be used to denote the network bit. The host bit. So this is the network ID, and this is the host ID. And we want to work out which IP addresses can we then allocate the devices on our network. So how do we do that mathematics? I say to you, 2 to the power x is equals to the number of networks, and 2 to the power y minus 2 is equal to the number of hosts per network. Okay, so let's look at the numbers in red. 1, 2, 3, 4. These are the remaining bits after the network ID. And I say to you, X is the number of bits for the network, or what we call borrowed bits, and Y is the number of bits on the host ID, or what we call unborrowed bits. So if you're trying to figure out how many hosts can I have on this network, we then say 2 to the power y, where y is the number of host ID bits, and we've got 4. So 2 to the power 4 minus 2 should give us the number of hosts on our network. So what is 2 to the power 4? We say 2 to the power 1, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 2 to the power 2 is 4, and 2 to the power 3 is 8, 2 to the power 3 is 8, and 2 to the power 4 is 16. So it means we can have 16 hosts minus 2, which is equals to 14. And why do we subtract by 2? It's because there are 2 addresses on the network that we need for every network. The first one is the network address, and the second one is the broadcast address. Every network needs those 2 addresses. They can't be used, they are there. So that's where you separate by minus 2. So what that means is we will have 14 hosts in this particular network that can then use that subnet to then either go to the internet or do anything that you want to do. So this is how we kind of calculate and do subnetting, which you're probably going to cover, I think, in the next 3-4 slides. We're going to get to the subnetting portion. And yeah, then we'll probably be able to call it a night. It's been a very long lesson, but I know the value of this concept of subnetting and the importance for us to be able to learn and derive value and, you know, try and be as practical as possible, because this is what you basically encounter. And the scenario that I've basically given to you is when you go to the ISP, they'll give you something like this. And then you need to carve out this IP address into smaller subnets for your organization so that you can use one for your email server. You can use an IP address for your email server. You can use another IP address for your You can use one IP address or a number of IP addresses for NAT to NAT your public IP address, sorry, your private IP addresses onto a public space. You can use, there's some systems, if you have VPN, your VPN server is going to need a public IP address. So you're getting from this whole block of addresses. So if this was a real world example, let me just erase that. If this was a real world example, so you've got 14 addresses that you can use. So maybe .1 becomes your VPN server. And then .2 is what you use for NAT for your public internet. And then .3 is what you use for NAT for your server infrastructure. And then maybe you've got an email server that needs a dedicated public IP address. So you'll have .4 being your email server. And some people have got public, file servers, FTP servers that they need to reach out. So you probably then allocate .5, to your SFTP. So this is how you basically would break such an IP address in real life, in a corporate environment, so that you've got, and then you might leave 6 up to 14 as reserved to be used at a future date. So very important. I think I've said that a couple of times. This whole topic is very important. Anything that we cover today is something that you probably need to know, because it's going to come and bite you at some particular point. All right. So we understand that part. And this was the table, full notation table. Just keep it in your mind. And we spoke about the wasting of addresses. And then this one, just a quick quiz. If I gave you a subnet mask of 255.255.240, what is the prefix notation? If I gave you a subnet mask of 255.255.255.240, what is the prefix notation? This is my answer. Your notation would be /28. If I gave you 255.255.240, yes, .0, what is going to be your notation? Your notation here is going to be 20. And if I gave you a subnet, what is the subnet for the /27 prefix notation? And that would be 255.255.255.224. So you're probably wondering, how did I get to this? And if you're lost, let's work together. So here we've got the subnet value, and we're looking for the notation. And we said, how do we calculate? We are adding our binary values. And by looking at this 255 address, it basically, I know on the top of my head, it's the whole octet. So the first one is 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot. So now I have 24, right? 240 is 128 plus 64, because wherever we've got a 1, we have to add. So 128 plus 64, 192, plus 32, 224, plus 16, 240. Remember, 128, 64, 32, 16, 8, 4, 2, 1. So our ones stop here. I count the number of ones going to the left. I have 24 plus 4, 28. That's how I came up to this 28 notation. With this one, the first 8 bits, the second 8 bits, 16, and then the third one, I'm using 4 bits to make 240. So that becomes 16 plus 4 to give us a /20. And then the last one is, we are doing the reverse. We have the /27, and we are saying, what do we mean by /27? We simply mean at the boundary of the 24, 128, 128, 64, 32, 16, 8, 4, 2, and 1. 24, 25, 26, 27. And when we add this, that gives us 224, and we've converted it the other way around. So that is important for us to understand. So that was basically my short quiz, just to be able to just try and reinforce and make sure that, the concept has not left us. And I covered this. This is just a reminder. Please just be aware of that increment. And now we're getting to I know it has come a bit late, but we're getting to the exciting part of subnetting, right? Where we start borrowing bits to be able to then create our subnets. And for us to subnet, these are the 5 questions that we need to answer. I am not the originator of this method. This method, I learned it from Todd Lamley. I think it was the CCNA 6th edition book. He explains this concept of subnetting in detail. And if ever I found a simplified method of subnetting, this one has basically been the best. I have not seen anything else in the industry that simplifies it. There's something known as ending, but it's not as simple as this particular method. So let us see what is covered. So he says, if we want to subnet, we have to answer 5 questions. The first one is, how many subnets does the chosen mask produce? The second one is, how many valid hosts per subnet are available? The third is, what would be the valid subnet? What would be the broadcast address of each subnet? And what are the valid hosts in each subnet? These are the 5 questions that we're trying to answer. So let us see how we do that. I gave you the formula earlier on. The number of subnets is 2 to the power x, where x is the number of borrowed bits or the number of ones. Very important, right? 2 to the power x, where x is the number of borrowed bits or the number of ones. And I said to you earlier on a /8 network or notation, how many ones do we have? We have 8. So 2 to the power 8 then gives you the number of networks. Subnet is equivalent to network. So when you say subnet, you're basically referencing to a network. So hello, Savage. Welcome to the class. Right, so 2 to the power what? 8. This is when we are subnetting on the class 4 boundary. However, when we do subnetting, 90% of the times, we are not subnetting on the class 4 boundary, but we are borrowing from the class 4 boundary. And I'll probably explain what I mean by saying we are borrowing from the, from the class 4 boundary. So in the earlier example, I said that we go to the internet service provider. They will give us a 192.168.100.0/28 address. So this is what they gave us, right? Let's work with that example. So they gave us this. So when we are subnetting, how did they carve this out? If we go to the 24 boundary of a Class C address, which is the 192.168, it's a Class C, it would end on a /24, right? The first 24 bits. So now the last 8 bits were denoted for the host ID, and the first 24 bits were denoted for the network ID. But because we want to carve up this niche network, what we have done is we have then borrowed, right? So we've got 8 bits. We went and borrowed the first 4 bits of the address and converted them into the network part of the address, and then left the last 4 bits as the host part of the address. So because we borrowed the first 4 bits of the last octet, that the borrowed bits then become our X value, and the unborrowed bits then become our Y value. So we can now take those values and then put them in the formula and then be able to then get how big our subnets are going to be and what are going to be the IP addresses in those particular subnets. And that's what we are going to look into in the next example. So if we borrow 3 bits, right, 2 to the power 3 is equals to 8. So before we subnetted, or before subnetting our address, this is what our network mask looks like. We are dealing with a /24. Why? Because the first 24 bits is there for the network ID, and the last 8 bits is there for the host ID. But we want to carve this IP address block into something smaller that we can share across the organization. So we are going to borrow 3 bits. And remember, the first question on the 5 questions was, how many networks do you want? Now I'm going to jump. I have a slide later on that was probably going to cover this aspect, but I'm going to bring it down a bit earlier. What we're doing here is you go to a pizza shop, right? You go and buy a pizza. Now, if it was the 2 of us eating that pizza, we could cut the pizza in half. You take 1 half, I take 1 half. Because it's the what? It's the 2 of us. And all of us will have an equal share. But if it was the 4 of us, we can't cut the pizza into 2 halves, because what happens to the other 2 people? So we are going to cut our pizza into 4 slices so that each one has a slice. If we are 8 of us, we then cut the pizza into 8 slices. Now, what has happened in this process? When it was the 2 of us, each of us would have had half a pizza, which was going to be, large enough. But when we are 4 of us, we are now cutting the pizza by 4, so the quantity is reducing, but we are having enough slices for everyone. When we are 8 of us, we cut the pizza into 8 slices, the quantity has further reduced, but there's enough slices for everyone. That is the same concept with subnetting. When you subnet an IP address, what you're basically doing is you are shrinking the size in order for you to cater for multiple smaller subnets so that you can then be able to design your network in a way that is more not cost effective, but effective for the objective that you want to achieve. So keep that in the back of your mind, right? That when we're subnetting, we are trying to shrink, and the only way we can shrink is by borrowing bits and manipulating that whole process. So in our case, you can only borrow from the host portion of the IP address. You can't borrow from the network portion because that has already been set, right? You have been given the host portion. That is where you then do the dissection from. So what this question is saying is you need to start asking yourself the question, how many networks do I need, right? How many people do I need to share this pizza with? And that answer is going to determine how many slices you're going to then cut the pizza into, depending on who you're sharing it with. So in our case, we are looking for 8 networks, right? So if we're looking for 8 networks, the next question is, what power of 2 do we need to get the networks that we require? And we say 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 3 is, 2 to the power 2 is 4, and 2 to the power 3 is 8. So 1, 2, 4, 8. So we are looking for 8 networks. So if we're looking for 8 networks, what value are we raising 2 to the power of to get the 8 networks? We're raising it to the power of 3. So thus, we are borrowing 3 bits from our network, from our host ID. And in the old subnet, we had 8 bits that were reserved for the host ID. When we borrow 3 bits, how many remain? 5 bits remain. So we borrowed 3 and 5 bits remain. 2 to the power 3 is 8. So we've got 8 networks. Now, how many hosts can we have per network? And the number of hosts per network is 2 to the power y minus 2, where y is the number of unborrowed bits. So if we borrowed 3 and remained with 5, the number of hosts then becomes 2 to the power 5 minus 2. And when you raise 2 to the power 5 minus 2, remember, if we come back again, 1, 2, 4, 8, 16, 32. And this is 2 to the power 1, to the power 2 to the power 0, to the power 1, to the power 2, power 3, power 4, power 5. So 32 minus 2 gives us 30 hosts. So when we borrow 3 bits, we create 8 networks, and each network will have 30 hosts per subnet. And that probably takes us to just a second. Right, so that then takes us to this slide. What are the valid subnets that we have? And the formula for that is 256 minus the subnet mask, which is going to be equals to the block size or the incrementing value. So how do you calculate that? We borrowed 3 bits. So the 3 bits that we borrowed are into the next octet. And we, from the left going to the right, it's 128, 64, 32, 16, 8, 4, 2, and 1. So we borrowed 3 bits, so 1, 2, 3. This is where we put our ones and the rest are zeros. So what is 128 plus 64 plus 32? It is equals to 224. 224 subtracted from 256 gives us 256 plus minus 224 is equals to 32. So our networks are going to increment in 32s. So the first network is going to be 0 up to 31. The next network is 32 up to 63. The next network is 64 up to 96. The next one will be 96 up to 128, all the way until we get to 224. That is how our networks are going to increase in size. So whilst we were given 1/28 block or /24 block, we can then carve it into smaller pieces, and then we can then give this range to sales. We can then use this range for marketing. We can use this range for engineering. We can use this range for management. We can use this range for finance. And all these become separate subnets in our organization. And we can then put rules to stop the subnets to be talking to each other, allowing us to implement controls, something that would be difficult or impossible to do if the network was a flat network. So when you subnet, you start achieving things like security, you start achieving things like segmentation, you start achieving things like VLANs and different VLAN subnets, because you have the ability to then decide the smaller block that you need, and you can get as granular as the number of IP addresses that you basically require. I'll probably use some real estate somewhere at the bottom, probably you can see. This is a scenario that you find quite a lot in networks where we have point-to-point networks, right? Point-to-point networks use 2 IP addresses because these are 2 devices that are basically talking to each other. And you want to be able to then come up with a subnet that just caters for that whole small portion. And this whole concept of subnetting then allows us to be able to then narrow down to that particular point. But once again, we can't learn by using one example, right? Repetition deepens impression. So we need to look at other examples to make sure that this whole concept is getting through. So what is going to be our broadcast address? And the broadcast address is the number before the next subnet. And we said our subnets are increasing in 32. So the first one is 0, the next one is 32, the next one is 64, 96, 128, 160. The broadcast address is going to be the number before the next subnet. So in this case, 31 becomes the broadcast address for subnet A. For subnet B, 63 becomes the broadcast address. For subnet C, 95. So it's the number before the next subnet. That is the broadcast address. And it basically goes through as you go along the lines. And the valid hosts per subnet are the numbers between the network address and the broadcast address, because those are the 2 addresses that we can use. The network address is always the first address in a subnet, and the broadcast address is the last address in the subnet. So in this case, 0 is our network address, and 31 is the broadcast address. And what is in between? 1 to 30. So 1 to 30 become the usable IP addresses. On subnet B, 32 is the network address, 63 is the broadcast address, and what's in between 33 to 62? That's what constitutes the usable IP addresses. And in the third subnet, 65 and 94 is what sits in between. And I think that's probably the second last question that we need to answer in this whole, questions about subnetting. So where does this all fit in? We spoke about this breaking down of networks. Why does it matter? It's because in your organization, you're going to have a router, and you're going to have departments. And by subnetting the different subnets and breaking them down, like I said, this then becomes sales. This then becomes, engineering. This can become marketing, and this can become the server VLAN or server subnet, whatever you want to call it. And because you have segmented it at layer 3, you are able to then put controls on who's allowed to talk to who. So you might not want inter-department communication, meaning there is no need for someone in marketing to be trying to access a PC that is sitting in engineering. Vis-a-vis, they should not be able to access a PC sitting in sales, because you want your sales numbers to be confidential and they don't get leaked. Under engineering, you want your R&D to be secured. So you can now put an access list on inbound traffic, and then you can then deny marketing and sales, but allow the server subnet to be able to come back and talk to the engineering network. And you have achieved that by subnetting by carving out your IP address into smaller subnets that then make sense to what you're trying to achieve as an organization, and you can then be able to implement it. And then at the bottom, I have created a table that just makes the process much more simpler, because then you can use this table to say, okay, what is my network address? 0. What is my first host address? 1. What's the last host address? 30. And what is the broadcast address? 31. The next subnet will be, network address will be 32, followed by the first host, 33, last host, 62, and the broadcast address of 63. So we've covered a lot in the last probably 2.5 hours. I am probably going to close it off at this particular point, just to give us enough time to, reflect on the content that we've basically covered, because there's a lot of information. We might have covered a lot of it not in a rush in a way, but just take time to, watch again if you've got enough time, and try and, practice as you go along the way. Next week, I will finish off the latter part of IP addressing. We'll probably relook again to the whole concept of subnetting and how we subnet. And if you have any questions, feel free. I'm probably just going to put my email address on the screen, just so that if you've got any questions, for those that might be joining us for the first time, Let's put that. Looking for. Okay, this is the one, right? So for those that are not aware of my email address, that's the one on the screen. So don't hesitate, send me an email. I will be able to at least prepare and answer questions before the next class. But just recapping what we basically covered, right? We looked at what is an IP address, and we said an IP address is just like any address that we deal with on a day-to-day basis. We have a home address, which is what identifies our house in a particular neighborhood. We then said the home address has got a structure. We've got the house number, we've got the street name, we've got the suburb that you stay, we've got the postcode, you've got the state and the country. And we looked at the email address and said we have the username and we also have the @ and the domain name. Similarly, we have IP addresses in the networking world, and we said IP addresses have to be unique in each organization, because when there's a conflict, then traffic can be able to flow as expected. So it is important for us to be able to make sure that we monitor. We looked at the different classes of IP addresses. We said there's a class A, class B, and class C. We looked at the process of converting from binary to decimal and vis-a-vis. And we closed off by now starting to look into this concept of subnetting to try and make sense as to why do we need to subnet and when do we need to subnet. And that's what we're going to cover in the next lesson in more detail. And then we can then look at IPv6. So once again, thank you for taking your time. And I hope and trust that the content made sense and it can help you along the journey. As I've said now, and I'll say it again, and I always say it, if you've got any questions, just hit me up. I will be able to respond, or I will address those questions in the next lesson. So yeah, thank you very much for taking your time and for joining me. And I look forward to the end of the 6 weeks that we can have derived value in this particular course. So that's it for now. Up until next week, Tuesday. Take care, and I will see you. Thank you for watching, and I will see you in the next one.